Let's look at one or more example of using Green's theorem to calculate an integral that is over a curve that goes along 2x and 2 square root of x oriented counterclockwise. Now we got sine x cosine y dx. And then the second component is 16xy plus cosine x sine y dy. Okay, let's visualize the curve. We already know that the orientation is counterclockwise, so we do not have to switch sign. Now, to figure out what is the region between the two graphs, we gotta know when 2x is equal to 2 square root of x. But that's actually pretty easy to see. First of all, one of the solutions is gonna be 0, which is obvious. And the other solution, which is also pretty obvious, would be x equals 1. So when x equals 1, those two are the same. All right, so let's just say that this is 1, this is 2. Let's say this is 1, this is 2. So at 0, both of the curves are 0. At 1, the 2x is going to be 2 right here, and also 2 square root of x is going to be 2, right? And so 2 square root of x would look something like that. So this is the region we're talking about, this region in between. And let's label the curves. This is 2x, this is 2 square root of x. All right, so first of all, in Green's theorem, you want to denote this part by p, and then this part by q. And it looks kind of complicated, but I'm thinking some things are going to cancel. So if I take q with respect to x, that'll become 16xy, that will be 16y, because remember 16 and y are treated as numbers, plus cosine x sine y with respect to x. Sine y is a number when you're treating it, right? When you take the derivative with respect to x, and derivative of cosine x is actually minus sine x. So this will become minus sine x sine y. All right, now p with respect to y will become, so sine x cosine y with respect to y will become negative sine x sine y. Okay, so in this case, we're treating sine x as a number and integrating cosine y, which is negative sine. Okay, now when we subtract these two, so let me fill this out right here. Sine x, sine y with the negative, and then this is 16y minus sine, minus sine x, sine y. Okay. When we subtract them, I think the good news is going to be that this term will cancel, right? Because you're going to be taking 16y and then you're subtracting py according to Green's theorem, which will become a plus sine x sine y. So that will just cancel out, yay. So all we will need to integrate is just 16y. All right, now to set up the double integral, we need to remember that this region is actually a type 1 region. So let's recall how to do that. So let me erase this right here. Okay, first of all, we are integrating 16y dy dx. The x limits are always the extreme values of x. So here x changes from 0 to 1. So this will be 0 and then this will be 1 right here. Now, here it'll be bottom curve to top curve. It is pretty easy to see that the bottom curve is 2x and top curve is 2 square root of x, okay? All right, so this will be 0 to 1, and then this is 2x, and then that's 2 square root of x. All right, and next we, of course, would have to integrate it. So let me do the integration over here. We are integrating 16y dy dx 0 1 to x 2 square root of x. Now this integral is not splittable because the limits are not numbers. We got variables in them. So we do have to integrate. And the inside integral with respect to y will become, remember y is y squared over 2. So this will become 8y squared. And we substitute y equals 2x, y equals 2 square root of x. Okay, so first let's substitute the top limit, which will become 4, right? So 2 is also squared, 4, and square root of x squared is x. And then we subtract minus 8, and y squared will become 4x squared. Okay, let's just simplify this. 8 times 4 is 32. Okay, integrating that with respect to x becomes 32x squared over 2 minus 32x cubed over 3. And we're substituting 0, 1. So I get 32 over 2 minus 32 over 3, which is the same thing as 32 over 6. Probably can possibly simplify that. So this will be like 16 thirds, I think, something like that, but that's it.